Okay, folks, so we just finished talking about what conditions we have to meet to be able to do a confidence interval on the proportion. Now let's do an example, start to finish. Is the proportion of nearsighted elementary age children now different than the historical amount of 25%? We randomly sampled 100 children from each of 5 randomly selected elementary schools, and their eyes were tested. Of the 500 children tested, 152 tested as being nearsighted. Construct the 95% confidence interval and answer the research question. So just a quick reminder, the formula that we're using is the formula for the confidence interval for the proportion, for P. And that formula is P hat plus or minus our Z associated with our confidence level times the square root of P hat times 1 minus P hat over N. So those are the variables that we need to be able to do the confidence interval. And just a quick reminder, P hat is equal to X over N. So state or calculate the given information or the numbers we need to do our math. So we need X, N, or P hat. Any two of the three, we're going to go ahead and do all three. So X in this case is the number of children who are nearsighted. So that's 152. N is the number of children who were tested in the new survey. That's 500. So P hat is 152 over 500. And I don't really care what that is in decimal form. You can figure it out if you want to. You can use fraction or decimal here for the math we're going to do later. And then we need to know our percent of confidence. In this case, we want a 95% confidence interval. And then step 2 is to satisfy our conditions. And remember, our conditions are 1, random sample, and I'm just going to write RS. 2 is binomial. And for the binomial, we have to have 2 outcomes. We have to have a set sample size. And we have to have independent trials. And then the third condition is normality. And condition 1 is that N times P hat has to be greater than or equal to 10. And N times 1 minus P hat has to be greater than or equal to 10. All right, so let's start working on these. So we are told that these children are randomly selected. So that is good enough to get us a random sample. We are told they are randomly selected. For binomial, do we have 2 outcomes? Well, kids are either nearsighted or not. And so that's a yes. We have a set N. We know that N is 500 for this particular example, so that's met. And it's independent. 500 children compared to all the children in the United States, definitely small, so that would be independent. And so we met the binomial condition. And then the next part is that we have normality, and that's N times P hat has to be greater than or equal to 10. And there's a little hat there, by the way. You just can't really see it. N times P hat is 500 times 152 over 500, and that is 152, which is always X in the confidence interval example. And then the next one, 500 times 1 minus 152 over 500 is always N minus X, or 500 minus 152, which is 353. And so these two are X and N minus X when we're doing for the confidence interval. We're going to have another scenario where these are not x and n minus x anymore out when we get to a new module. So that just makes the math easy there. 152 is definitely bigger than 10. 353 is definitely bigger than 10. So normality is met. When we can satisfy these three conditions, we can do a one proportion the interval. So we've met the conditions to do that and use the formula that's up here. All right, so now that we've met those conditions, we can do this in R. So the code in R is going to be prop.test, parentheses, and then you put in x, comma, n, comma, alternative equals two dot-sided in quotes, comma, confidence level equals whatever your confidence level is in decimal numbers, comma, correct equals false. And we'll talk about this correct equals false in just a minute. So for our scenario, we're going to have prop.test, parentheses, x for us was 152, n for us is 500, and we don't say x equals 152 and n equals 500. We just put the numbers in, so order matters for those two. I think for the rest of it, it doesn't. You can put the other three things in any order and it's fine. Then we'll do alternative equals two dot-sided. And you'll learn what this two dot-sided is in the next module. And then confidence level is whatever type of confidence interval we want. In our case, it's 95%, so we have to put that in decimal form, 0.95. And then correct equals false. We will always use that in this class. We'll talk about why in just a few minutes. I'll come back to that. All right, so I've got R open, and in this example, prop test, we're doing this line of code. Notice I don't have to import any data. I've already counted the number of successes and I have n. If I had raw data that just listed nearsighted, nearsighted, farsighted, neither, nearsighted, nearsighted, farsighted, neither, I'd have to count all of the nearsighteds and then I'd have to subtract that from n. So I'd have to count all of my data to be able to get these numbers using a frequency table. So I don't have that because I don't have the raw data. So run the code prop test of 152, 500, alternative is two-sided, confidence level is 95%, and correct equals false. And when we run that, we get the output down here at the bottom. And this output is a one sample proportions test without a continuity correction. We'll talk about the continuity correction in a little bit. And I'm not going to talk about the top stuff because we're going to talk about that in the next module, but we do get the 95% confidence interval out of this output. So the 95% confidence interval is 0.2653 to 0.34568. And we can write those down and then we'll just round them and make them percentages. So let's write those down, 0.265, and let's do 0.346. So our confidence interval is 0.265 is our lower bound, and our upper bound is 0.346. And if we want to change this to a percentage, we would have 26.5% is less than our true proportion is less than 34.6%. So when you do these problems, it's okay to leave the problems in decimal or percent form, but we typically put them in percent form. This is our estimate for the true proportion. So the interpretation step is I am whatever percent confident. In our case, we did a 95% confidence interval. So I am 95% confident that The true proportion, that should say population proportion. The true proportion or the population proportion, your choice which words you use, true or population proportion is between 26.5% and 34.6% of children who are nearsighted. And so somewhere between 26.5 and 34.5% of our children are nearsighted. That is higher than the 25%. This is higher than the historical value of 25%. So this is the answer to the research question. We don't always have a research question. Sometimes we just want to estimate the parameter. In this case, you were given something to compare to. All right, let's do the next example, but we're going to talk about Yates continuity correction first. So some books will use the Yates continuity correction to calculate the test statistic and the p-value of the hypothesis test on a proportion. This is also true when we do the confidence interval. It is specifically used to correct error introduced when moving from a discrete distribution to a continuous distribution like the normal. Um, this is really important when P is close to 0 or 1, or N is not very large. You should know this exists, but we're not going to use it in this introductory class. So we will always use the command correct equals false when we're doing our confidence interval on the proportion. You should also know that there is no function in base R that calculates a hypothesis test or a confidence interval using the normal approximation method. It uses a different distribution, but answers are going to be remarkably close to what we'd get with our formula above. So we won't worry about the differences here. Just know that you can use the normal curve, or you can use what they're calling is a chi-squared curve. We're going to see a chi-squared curve later in the semester. All right, so let's do another example. It is believed that group projects help college students prepare for the team environment required in many jobs after college. The Community College Survey of Student Engagement reports on the proportion of students who've worked with classmates on a group project in the current academic year. A random sample of 300 students is polled, and 174 students did work on group projects this year. Construct the 90% confidence interval for the true proportion of students who've worked collaboratively on a project this academic year. So step one is to do our given information. And my given information, I need X, N, and or P hat. I don't really care. I have X is 174 students. N is 300 students. And if I have those two, I can get the third one of these. That's 174 over 300. And then I need my percent of confidence. That's 90%. And then I need my conditions. And remember, there are a bunch of those. The first condition is random sampling. The second condition is binomial, random variable. And for the binomial, we have to have two outcomes. N is a set number and independent. So I'm going to leave a blank there. And then the third one is normality. And we have to show that too. So I'm going to use a different color for those. Random sampling. So we are told it's a random sample. So that condition is met. They either worked on a group project or not. We have a set number of trials, N equals 300, and they should be independent because 300 is way smaller than the number of students in community college. So binomial is met. Normality, we need to show that n times p hat is greater than or equal to 10. And remember, that's just x. You could do that math there if you wanted to, or you can remember that it's x. N times 1 minus p hat has to be greater than or equal to 10, and that's n minus x, which is 300 minus 174, and that's 126. Both of these numbers are greater than 10, so the normality condition is also met. When that happens, we are allowed to do a one proportion z interval. All right, so the next thing we're going to do is we're going to calculate the z interval using R. So we're going to go to R and do this now. So let me move to R. I've already got the code written. So we're doing the group project example. We're doing prop.test of x, which is 174, n, which is 300. Alternative equals two-sided in quotes. My confidence level, conf.level, is 90, so 0.90, and correct equals false because we are not using Yates in this class. So we run it and we get our output down here. The 90% confidence interval is 0.5326 to 0.62595, and I'm going to write those down. So my confidence interval is 0.5326. That's the lower bound for the true proportion P. And the upper bound is 0.6260. And so then I have to do my interpret step. Step 4 is the interpret step. And I am whatever percent, in this case it's 90% confident, and I do CONF for confident, that the true proportion or the population proportion, the true proportion P of students from community college, I'm going to do CC for community college, who worked on group projects was between, and I'm going to do whole numbers here, 53% and 63%. All right, that's it, you guys.